So at this point, it may seem like we know pretty much everything that we need to know to understand the shape of different graphs. But we should note the following, that there is some other information that may be helpful. Let me quickly try to sketch out why this is the case. Let's suppose that I know that on a given interval, I have a function that is increasing. Well, I can draw a function that's increasing that looks like this, but I could also draw a function that's increasing that looks like this. And these are very, very different shaped graphs. And so I may want to understand a little bit more about how my graph bends. And this is summarized in the idea of what we call concavity. So let's take a look at what we have over here. If f is differentiable on an open interval, then f is said to be concave up on an interval if my derivative, that is my f prime of x, that is the slope of my tangent line, is increasing on an open interval. Okay, that's kind of weird. Concave down, my graph would be concave down if on an open interval my derivative is decreasing. That is, the slopes of my tangent lines keep getting smaller. Okay, this is really, really weird to try to imagine, but let's go ahead and try to start with at least figuring out what a picture with an increasing first derivative would look like. So we know here that concave up means that I should have increasing slopes. My slopes should be increasing. They should be getting bigger and bigger and bigger slopes. So let's imagine, for the sake of argument, that I draw the slopes of my tangent lines, and they have to keep getting bigger. Okay? So like maybe I start with a slope that looks something like this. Okay, I'm not drawing the function, but a tangent line I could imagine on it. Now this is a slope that's negative. So if I wanted to make it a bigger slope, I could make it like less negative. If I wanted to make that bigger, I could make it less negative, and maybe then even slightly positive, and then maybe more positive, and then maybe very positive. Notice that my tangent lines are kind of getting larger over time. But then if I was to try to sketch a graph that kind of might fit this particular shape, notice that I have a graph that's kind of angled in this direction. And this is the direction of a curve that is concave up. In the same way, I could see that if I had a graph that was concave down, that again would correspond to decreasing slopes of my tangent lines. So that would mean that I would need to have tangent lines that keep getting slopes that are smaller and smaller and smaller. So maybe I start with the tangent line that looks like this, but then the tangent line slope has to decrease. It's got to be less steep, and then maybe even less steep, and then maybe even a little bit of negative steepness, if you will. And then it's got to keep kind of getting more and more and more and more negative slope. Well, then if I think again about what the graph of something like this would look like, my tangent lines would be modeling the shape of a graph that does something like this. And so I can see here that I have concave up corresponding to increasing f primes, but that obviously means then that I'm going to end up with this sort of a shape on the graph, or potentially a shape that looks something like this if I kind of imagine only half of this. And concave down would give me a shape that maybe looks like this, or maybe only half of this, all right? Or one side or the other of this. So one of the easy ways that I tend to remember this is with the only rhyme that you will ever hear me give in any of my courses. And I hate doing this, but here it is. If a graph is concave up, looks like a cup. If it's concave down, looks like a frown. Okay, I hate that. It's the only time I'm going to say it. You can rewind the video and replay it as many times as you need. Okay, so here's how we can go ahead and start to kind of summarize all of this stuff into a nice theorem. If I want to check to see if my derivatives are getting larger, notice if I'm curious if a function is increasing, how do I check to see if a function's increasing? I mean, isn't that what we've been working on in all of our previous examples, is how I know when a function's increasing? Well, the way that I do that is by taking the derivative of my function. So this all of a sudden then gives us a need to actually explore our second derivative, or the derivative of the first derivative. If my second derivative is positive, that is, if my first derivative is increasing, my slopes are getting larger, then my graph is concave up on the interval. But if my first derivative is decreasing, that is, the slopes for my tangent lines are getting smaller, then I have a graph that's concave down. And so this is kind of summarized and then into what we call our concavity test. So let's go ahead here and take a look actually at example 5 to see how we could attempt to use this. I want to find the intervals where, small typo, find the intervals where my function is concave up or concave down. Okay, so let's see how this actually works. I would need, again, to start by calculating my first derivative. So we calculate that f prime of x is equal to, this is going to be what, x to the third minus 3x squared. But if I want to find concavity, I have to go to my second derivative. That's what the second derivative is good for, helping to find concavity. This is going to get me 3x squared minus 6x. Now I'm going to go ahead and pull out a common factor here. I'm going to be left with an x minus a 2. And again, if I want to find when f prime is increasing, I should find its critical values. So take its derivative and find where its derivative is equal to 0 or where its derivative is going to be undefined. So I'll see here that f double prime of x is equal to 0 when 3x times x minus 2 is equal to 0, which of course is going to lead me to x could be equal to 0 or x could be equal to the value of 2. I can also see here that f double prime of x is never undefined because, of course, it's a polynomial and no value I can plug in for x will ever cause this to be undefined. So again, I'll draw a nice little picture here where I'm going to calculate plug in my x's and my f double prime. So I'm going to have x is a 0 and x is a 2. Here I know the second derivative is equal to 0, and now I can see if I'm going to get tangent lines that are increasing in size or decreasing in size. So let's see. If I plug in a value like, say, -1 into here, notice I'm going to get a negative and a negative, which is going to give me a positive overall result. If I plug in a value like 1, I'm going to get a positive and a negative, which is going to give me a negative result. And if I plug in a value like a 3, I'm going to get a positive times a positive, which is going to get me a positive result. Notice that what I have here is not telling me, again, anything about whether the original function is increasing or decreasing, but this is telling me where the original function is concave up or concave down. So I tend to like to draw pictures like this. On this interval, the graph is concave up. On this interval, the graph is concave down. And on this interval, the graph is concave up. The second derivative is telling me about concavity. So let's go ahead then and see how we can summarize all of this. Our goal was to just find the intervals where this was concave up or concave down. And so we can say that f of x is concave up on the interval from -infinity to 0 and from 2 to infinity. But of course, it is concave down on the interval from 0 to 2. So this is the information that we actually have here. This is how I would go ahead and actually determine whether a function is bending in particular ways. So that's again how I can think about concavity. Which way is the graph kind of bending as it moves?